Good day, my name is Tibishes Vanda. Welcome to another Fluid Mechanics 101 presentation. Today I'm going to be talking about minor losses. So far we've calculated the pressure drop per unit length in a straight pipe. So that pipe didn't have any valves, any bends and stuff like that. We also calculated the total pressure drop considering several miles of pipe from a pump station to a storage tank. Minor losses in a water pipeline are classified as those pressure drops that are associated with piping components such as valves and fittings. Fittings include elbows and tees. In addition, there are pressure losses associated with pipe diameter enlargement and reduction. A pipe nozzle existing from a storage tank will have entrance and exit losses. All these pressure drops are called minor losses as they are relatively small compared to friction loss in a straight length of pipe. Generally, minor losses are included in calculations by using the equivalent length of the valve or fitting or using a resistance factor or K factor multiplied by the velocity head, which is velocity squared divided by 2g, which is your acceleration due to gravity. The term minor losses can be applied only where the pipeline lengths and hence the friction losses are relatively large compared to the pressure drops in the fittings and valves. And usually that's the case. You find that your pressure loss in the pipe itself it's huge in terms of magnitude as compared to those found in your valves. In a situation such as a plant piping and tank farm piping, the pressure drop in the straight length of pipe may be of the same order of magnitude as due to valves and fittings. In such cases, the term minor losses is really a misnomer, which means it's just in terms of calling it, but it's actually they are not minor. In any case, the pressure losses through valves, fittings, etc. can be accounted for approximately using the equivalent length, okay, times the velocity head method. So equivalent length, it means how much pressure loss would have been lost when compared to a pipe length, and I'll show that using an example. It must be noted that this way of calculating the minor losses is valid only in turbulent flow. Note that are valid for laminar flows and flows in industry. They are always or usually only turbulent flow regime. Valves and fittings. The following table shows the equivalent lengths of commonly used valves and fittings in a typical water pipeline. So we're given the values for L over D. Your L is your equivalent length, and this is the diameter of your valve. So for a gate valve, the ratio is 8, flow valve 340 etc. But you need to take a note that they made a mistake here. For a swing check valve, it's 50. It can be seen from this table that a gate valve has a L over D ratio of 8 compared to a straight pipe. Therefore, a 20-inch diameter gate valve may be replaced with a 160-inch long piece of pipe. So the pressure drop in this valve will be same as the pressure drop in the 160-inch long piece of pipe. That will make pressure drop through the valve, where L is your equivalent length, your D is your valve diameter. Example, a piping system is 2,000 feet of NPS 20 pipe that has two 20-inch gate valves, 3 20-inch ball valves, 1 swing check valve, and 4 90-degree standard elbows. Using the equivalent length concept, calculate the total pipe length that will include all straight pipe and valves fittings. Solution: we can convert all valves and fittings in terms of a 20-inch pipe as follows. So for a two 20-inch gate valves, remember the ratio is set for a gate valve is 8, so it's 2 by 20, which is the diameter by 8, so it's equivalent to 320 inch of 20-inch pipe. 3 20-inch valves is 3 of them. The diameter of the valve is 20, and the ratio is 3, so you get 1 inch and 1 inch of 20-inch pipe. 120-inch swing check valve is only 1. The diameter size by 50, the ratio, you get 1,000 inch of 20-inch pipe. 4 elbows is 4 of them, and it's equivalent to 20 each by 30, which is equals to 2,400 inch of 20-inch pipe. So total for all valves and fittings is 3,009 inch of 20-inch pipe, which is same as 325 feet of 20-inch pipe. Adding the 20 feet of straight pipe as we calculated in the previous presentation, the total equivalent length of straight pipe in all fittings is equal to 2,325 feet. So the pressure drop due to friction in the preceding piping system can now be calculated based on 2325 feet of pipe. It can be seen in this example that the valves and fittings represents roughly 14% of the total pipe length. So if you divide 325 over this one and convert to percentage, it's roughly 14%. In blunt piping, this percentage may be less than that in a long distance water pipeline. Hence the reason for the term minor losses. Resistance coefficient or K factor. This is the second method. Remember, we say you can use the equivalent length or the resistance coefficient, sometimes called the K factor. Another approach for accounting for minor losses is using the resistance coefficient or K factor. The K factor and the velocity head approach to calculate pressure drop through valves and fittings can be analyzed as follows using the Darcy equation. From the Darcy equation, the pressure drop in a straight length of pipe is given by H is equals to F L over D V squared over 2G. So the term F L over D, this term, right? Remember, F is the friction coefficient, L is the length of pipe, the diameter of pipe, this is the velocity, G is just the acceleration due to gravity, which is a constant. So that term may be substituted with the head loss coefficient K, also known as the resistance coefficient. And the above equation then becomes H is equals to K V squared over 2G. In the above equation, the head loss in a straight piece of pipe is represented as a multiple of the velocity head, V squared over 2G. Following a similar analysis, we can state that the pressure drop through a valve or a fitting can be represented by K multiplied by V squared over 2G, where the coefficient K is specific to the valve or a fitting. Note that this method is only applicable to turbulent flow through pipe fittings and valves. No data available for laminar flow in fittings and valves. Typical K factors for valves and fittings are listed in the table below. So this is the table of our different valves here. For the gate valve, if it's a 2-inch, so the K factor will just come here, 0.15. If it's a standard elbow, which is 90 degrees, and it's 1 inch, the value is 0.69, and so forth. Resistance coefficient or K factor. It can be seen that the K factor depends on the nominal pipe size of the valve or fitting. The equivalent length on the other hand is given as a ratio of L over D, equivalent length over diameter of valve for a particular fitting or valve. From the table, it can be seen that a 6-inch gate valve. So gate valve is 6-inch. Right, is a K factor of 0.12, while a 20-inch gate valve is a K factor of that 20-inch gate valve of 0.1, 18 to 24, yes. However, both sizes of gate valves have the same equivalent length to diameter ratio of 8. If you're using equivalent length, they will have the same ratio, whether it's a 6-inch gate valve or a 20-inch gate valve. The head loss through a 6-inch gate valve can be estimated to be 0.12 multiplied by the velocity head, and that in 20-inch is valve is 0.1 multiplied by the velocity head. The velocities in both cases will be different due to different diameters. As an example, if the flow rate was 1000 gal per minute, the velocity in the 6-inch valve will be approximately. So the outer diameter, I'll show you how to get an outer diameter of a 6-inch valve. Is close to 6.62 meters inch. So in thickness, it is that when you're using a schedule 10 pipe. So inner diameters, outer diameter minus 2 by thickness, you get 6.357 inches, which is 0.530 feet. Your flow is 1000 gal per minute. Convert that, you get 2.228 cubic feet per second. Then using the continuity equation, Q equals to V, you can calculate your V. If your Q is 2.228 cubic feet per second divided by R is equals to pi R squared. Convert that, your R is diameter over 2, so you get D squared over 4. Substitute, you get your velocity of 10.1 feet per second. Therefore, head loss in a 6-inch gate valve is 0.1 multiplied by the velocity head. Now we have the velocity, substitute there for 10.1 feet per second squared. That's our velocity squared. Divide by this, you get that a head loss of 0.1 inch. So if you do your math, then you can see what I'm talking about. For a 20-inch valve, outer diameter is 20, thickness 0.25 when you use schedule 10. I will show you how to use a table for that. So inner diameter, you get 1.625, right? Then our volumetric flow rate, you get that as before. Do your substitution, you get that. Therefore, head loss is 0.1 by V squared, which is 1.07 squared by that, which is 0.02 feet. So the head losses appears small since we have used a relatively low flow rate in the 20-inch valve. Usually it will be higher. In reality, the flow rate in the 20-inch valve may be as high as 6,000 gal per minute, and the corresponding head loss will be 0.072 feet. So remember, pipe size is specified by 2 designations: a nominal pipe size NP set for diameter based on inches, and a schedule for hole thickness. So the European ISO designation equivalent to NPS is DN, or nominal diameter, in which sizes are measured in millimeters. Usually valves, they're given in this designation. The term NB, nominal bore, is also frequently used interchangeably with NPS. So remember, we were told that the valve is 6 inches. I'll come here, then if you remember, use a diameter of 6.625, and if it's the schedule 10 where they intersect, is 0.134 thickness. We also used a 20-inch schedule 10. So the outer diameter is 20, the thickness is 0.25. You should note up to after 12 inches from 14 inches going outwards. NPS, nominal pipe size, is the same as the outer diameter, which is not true for anything from 1/8 up to 12. So you should take note of that. Pipe enlargement and reduction. Pipe enlargements and reductions contribute to head loss. that can be included in my analysis. For certain enlargement of pipes, the following head loss equation may be used. HF, which is weight loss, equals to velocity in pipe 1 minus velocity in pipe 2 squared over 2g, where V1 and V2 are the velocity of the liquid in the two pipes, sizes D1 and D2 respectively. Writing the above equations in terms of pipe cross-sectional areas A1 and A2 for certain enlargement, you get that your HF is equals to 1 over A1 over A2 squared multiplied by V1 squared over 2g. You can do the math. I actually did the math and trying to derive it, and I got the answer right. This is illustrated in the figure below. So there's a friction loss associated with this sudden pipe enlargement, and also with a sudden pipe reduction, there's a friction loss. So the A1 over A2 can be used to find the constant which you call CC, which for sudden contraction or reduction in pipe size, as shown in figure above, the head loss is calculated from HF is 1 over CC minus 1 multiplied by V2 squared over 2g. Remember this constant, as you can find by dividing area 1 over area 2, where the coefficient CC depends on the ratio of two pipes cross-sectional areas A1 and A2 as shown in the figure above. Gradual enlargement. Gradual enlargement and reduction of pipe size as shown in figure below cause less head loss than sudden enlargement and sudden reduction as we showed above. For gradual expansions, the following equations may be used. HF is equals to CC, V1 minus V2 squared over 2g, where CC depends on the diameter ratio D2, D1, and the cone angle beta in the gradual expansion. The CC is different from that of sudden enlargement or sudden contraction. A graph showing the variations of CC with beta and the diameter ratio is shown below. So for the CC, we use this gradual pipe expansion head loss coefficient table. For example, if your diameter ratio is 2 and the angle is 20 degrees, then your coefficient is 0.3. That's the CC you use here. Pipe entrance and exit losses. The K factors for committing the head losses associated with pipe entrance and exit are as follows. K is equals to 0.5 for pipe entrance, sharp edged. K is equals to 1 for pipe exit, sharp edged. K is equals to 0.78 for pipe entrance, inward projecting. That's if let's say water is flowing from a container going to a pipe, then to a pump, or you are filling your pipe. How is it exiting to the pipe? And all these, why do you calculate the frictional losses? You want to know your system pressure loss or your system resistance. We call it system resistance to flow. Then you can use that system resistance to flow to size the pump which is needed for that particular system. And most of the time I talk to people, they don't understand what's their system resistance. They just put the pumps haphazardly without studying or calculating their system resistance, and then it results in pumps which are undersized. Then you have many breakdowns of pumps which are oversized, and also you find that you're using too much energy. But as we go on with the presentations, I'll get to the point now where we are sizing the pumps using all this knowledge we've been trying to accumulate so far. And as always, thank you for watching. And if you have any queries, any additions, submissions, do not hesitate to contact me on my email address tuaspand@gmail.com. Please like, comment, and subscribe to my YouTube channel to learn some more of the engineering stuff. And I'll see you next time. Be blessed.